So here is a pencast about finished state machines. The goal of this pencast is to take you through the basics of a finished state machine. We would look at it in relation to the regular sequential circuit that we know. We'll get an overview of the functional blocks in a finished state machine. We will look at an important thing that is state diagrams. There is a self-study on ASMs. That would be another way of drawing states. We would look at a couple of types of output logic called Mealy and Moore and the differences between them. And then we'll look at state enumeration, how states can be enumerated. And there's a couple of different types of state enumeration that we will take a brief look at. Then there is a code example from the book, listing 5.1, that you are to work with. And if you want to read in the book, it will be in chapter 5.1 till 5.3. So when we talk about synchronous circuits in general, as we know, they can be informally split into three types. One type is called regular sequential circuit. A regular circuit is something that exhibits a repetitive or predictable behavior. That could be a binary counter or a shift register or some predefined function that runs the same manner again and again and always. Then we have what we could call a random sequential circuit. This could be one of the types we are to talk about now, that we can model with state machine, where it can exhibit different behavior depending on the surroundings and the surrounding inputs. The combined synchronous circuit is a combination of the two above. So a combination of the regular sequential circuit, that could be again a shift register or a counter or both, and then we combine them with the random sequential circuit. That could be the state machine, using that as a controller and controlling a couple of regular like circuits. One good example of that is the UART that you probably know from your embeds, and we are to work with that in the following lessons. This should not be something new. This is our synchronous circuit that we know. We have the state register here in the middle. We have the output logic over here. And then we have the next state logic that determines the next state based upon the current state and the input. So this is just catch up on what you already know about the synchronous circuit block diagram. But still, the synchronous circuit block diagram is the most important foundation for understanding state machines and how they work. This is basically an explanation of the synchronous circuit as told before. So if you want to read it, you can pause and go through it yourself, because we have talked about that many times previously. Here is an overview of a finite state machine, also called FSM. The finite state machine contains its random logic, as we called it, embedded in the next state logic. So whatever the next state logic does, we could call that the random logic part. That would be to determine the value of state next based upon what inputs we may have and what the value of the state register is currently. And as you'll see soon, we can model that with state charts, but this is the so-called random part. The state machine as a complete system is often used as a controller in a system. That could be, I think we talked about a diesel engine previously, what happens when it needs to set ignition and start preheating and cranking and running and things like that. Or it could be another engine system, or it could be some of your projects where you need a specific behavior during boot and initialization, and then you need another behavior once the system is up and running. You're not limited to having one finished state machines in a system. You can have a multiple in a system and they can run perfectly fine in parallel, or you can have one state machine embedded within another. As you can probably see over here, we have two types of output logic, namely mealy and more. The difference between the two of them are following. The more output, as you see here, is the value of the output is purely determined on what value the state register have. That would be what state is the system currently in, where the mealy output is based upon the value of the state register and also based upon the input. So does that mean that the more output logic cannot change according to input? Well, no, it does not mean that. It just means that the input would have impact on the random logic in the next state logic, and we would probably need more states to exhibit the same behavior with a more type of output logic than if we have a mealy output logic. That might sound like a drawback, but actually in reality more output logic is often the nicest way or the easiest way to implement a system, because, well, we'll see that later on. And just as mentioned before, on a more machine, or when we have more output logic, the output is purely a function of the system state, where in a mealy machine, or when we have mealy output, the output is purely a function of the state combined with the input. We'll see a bit more in the following slides on how we can implement the two different ways of doing output logic. As you can see, I've highlighted this as an important slide. This is how we can draw a state diagram to represent a finished state machine. The state diagram consists of a circle representing the state. It consists of a number of arrows that indicates the transitions from one state to another. The circle in the middle only represents one active state in the system, where we typically have, or we always have, multiple states, otherwise it does not make sense to create a state machine. Inside the state we have the state name, as you can see. I was trying to get a pointer. Here we have the state name. Then we have something called MO. MO means that is the more output value or more output logic, because as mentioned in the previous slide, more output logic only depends on the state or the value of the state register. So we can draw the more output assignment inside a state, because that's the only thing that drives it. On the other hand, the mealy output value is depending on the state and the input. The input in this case would be what causes a transition to one of the other states here. So the mealy output assignment would happen when we have a logic expression fulfilled that causes us to change from one state to another, or one state to a third. In this case, the mealy output assignments would be different. So this is an important distinction to have when we talk about state machines. And we can see how we want to implement a state machine based upon where we would draw the output logic assignment. More inside the state and mealy on the state transitions, or the arrows between the different states. So take a couple of seconds to think about this before we move on. This is a more complete state diagram with some really lousy state names. I think most of the book is good, but their way of naming states doesn't really make sense. States here are called S0, S1 and S2. As you can see, in this example we have both mealy and more assignments. We have more assignments in the states, state 0 and state 1 here. We have one single mealy assignment over here between state 0 and state 2. And then we have different Boolean conditions that needs to be fulfilled to get transitions between the different states. When we're in state 2, we always go directly back to state 0, and that is symbolized by having a transition without an event associated with it. So the lesson learned here is basically because state machines is a good way of representing how a state machine works. Just like you do module design, always, not sometimes, but always draw a state diagram before you start to code. If you remember this, you'll keep your teacher happy and your classmates and whoever you collaborate with, and it would also make life easy for yourself once you need to revisit your documentation. There is one more and a bit more complex but a bit more efficient way of drawing states. They are called ASM charts, and it's actually meant to be a self-study, so I would recommend that you look it up in your Prototyping by VHDL examples book. Spend perhaps 20 minutes reading that chapter and pausing this video, and then return to the video once you're done. So once you're done browsing through the book for ASM chart examples, there's also some PDFs called ASMD on Blackboard that compares the simple state chart form with the ASMD chart form, and you should go through that as well to get some practical examples of how ASMD charts can be used, because they are very easy to implement from once you get the main idea. So, a couple of words about state enumeration. State enumeration is basically just about creating your own type keyword, or similar to creating your own data type. We call them state types here. And typically you create two signals called state rec and state next, so they comply with the figure we know of the synchronous system. These two state signals are based upon our state enumeration. State enumeration is created by writing type and then the name of the state type we want here, and then here is one of the few very bad examples in this book. The naming of states, they use small letters and they call them something as non-informative as S0, 1 and 2. Apart from that, the chapter on state machines is very good, but I would very much suggest, I would almost command you to use meaningful names like shown down here. If you have a system that have these states, of course, otherwise they would not make meaning. But please do use capital letters and call the states meaningful names. They do not take up any more space because they have long names. It just makes it much easier to understand your code. Instead of having state 0, 1 and 2 like up here, it doesn't make any sense when you try to understand how the behavior of the state machine is. So use capital names, that makes code reading a lot easier. So if we should try to relate some example code of a state machine to the synchronous system, we could look in this figure here. In this figure we have some code on the top, and we have our synchronous system down here in the bottom. What is shown marked in green is the state register. The state register is composed of a register and two signals, state next and state rec. And as we can see up here, if we do not have an active reset, then state next that comes out of the next state logic would be transferred to state rec, so that becomes our next state value. If reset is active, in this case it would be assigned the not so meaningful name S0. I would assume that we here have a state name that would be something like init or idle or whatever handles initialization of our system. But apart from that, this is what makes up the state register. You might come across different enumeration schemes when we talk about how state names are translated into bit values. They typically pop up in the ICE console once you press synthesize your design or press implement. There are a couple of different ways this can be done, with binary assignment, gray code assignment, one-hot assignment, or something called almost one-hot assignment. This is just the way that the different states are translated into bit patterns, and if you do very high-speed designs, there would be some potential advantage in using this one-hot assignment. Even though it takes up the most bits, it can be most efficient in a very high-speed design. But for now, it doesn't really matter what type of enumeration scheme that Xilinx ICE will use to assign to the states. So here is shown our next state logic, and again, as you recall from the figure on the previous page, the next state logic is what determines our state next variables or signals name, and it determines the next state based upon what state we are currently in. Therefore, we have a case routing, what's called a routing statement up here that looks at the state register, and depending on whether the state register is in state S0 or state S1 or state S2, it would evaluate different inputs to determine the value of the next state. And if we go back a couple of slides, or if you have the slides separately, you can look at the state chart we saw 5 or 6 slides back. That's what implemented this functionality. When we are in state 0, depending on the value of A and B, we can end up either in state 2 or state 1. And if A is not set to 1, then all this doesn't matter, and we will remain in state 0. If we have entered state S1, we again look at the A input. If it is true, we would return to state 0. If not, then we would go to state 1. Sorry, we would stay in state 1. If we are in state S2, we would always return to state 0. This matches exactly what was shown in the state diagram, and this is basically how you implement the next state logic. The output logic is left out here because it is handled separately in its own process to make it explicit that this is the output logic instead. Here you see the state diagram again, and it implements the exact same functionality regarding state 0, 1 and 2 and the events that causes it to go from one state to another. So again, if you start out with modeling your to-be state machine with a state diagram, you can quickly change it on a piece of paper and try to step through the transition from different states to different states and back again before you implement it in VHDL. So coming up is 2 different examples of output logic, where the first one would be more output logic. More output logic, as you probably recall, depends only on the current state of the system, so it is directly a function of the current state in the system. In this case, we have only one signal to assign, that would be y1. If we are in state S0 or S1, y1 gets the value 0. If we are in state S2, y1 gets the value 1. So it doesn't take up much, but because it is in its own distinct process, more output logic can be implemented rather simple by looking at what state is the system in. So take a few seconds to look at this in relation to the state diagram before we move on. So the other type of output logic we could have is the Mealy output logic. The Mealy output logic, as you recall, is a function of the current state and the input. So here we look at both the current state and we look at the input. That also means that our Mealy output values are assigned together with transition from one state to another. So the output logic is over here, the code. We can see that we evaluate the current state, inputs A and B, and if we are in state 0, we evaluate A and B. If they are both true, y0 gets assigned the value 1. If that's not true above, then y0 gets the value 0. If we are in either state S1 or S2, y0 gets the value 0. So this is also pretty simple in this case, but we need to take in consideration both what state are we currently in and what values do the input have. So I would definitely recommend that you try to use more output logic and model enough states in your system so you can handle it all based purely upon states, but Mealy output logic is also an option. So to round up, Mealy versus Moore. The Moore machine, the output is a function of the state. The Mealy machine, the output is a function of the state and the input. And if you look at it theoretically, or what can I accomplish with one compared to the other, both Mealy and Moore have the same computational power or capability, you could say. You can implement the exact same things. It's just a matter of taste and how you split up your design and how you create your state machines. Now it's time for you to do a little bit of a lab. Find listing 5.1 in the book and create a test bench around it. Spend half an hour or so figuring out, in terms of performance, what is the difference between the Mealy implementation and the Moore implementation of the output logic. So dive into that and work with it for at least half an hour, and we can discuss it before we move on in class, and you can watch the rest of the video once you have started up. So if you haven't quite spotted yet what's the difference between the Mealy and the Moore implementation, you could in your simulation look at some of the things regarding to assignment of the outputs. We have y0 and we have y1 that both get assigned based upon what state we're in. Actually, both of them get assigned to the value 1 based upon the same input, but we can see assignment of y1 happens previously y0 gets assigned before y1, and there is a reason for that, and I would like you to identify that in the code. So that could perhaps look like the Mealy implementation is performing better, and in some cases it might, or at least it might perform faster. But then there is one important thing we need to remember again. That important thing is called the setup time for a D flip-flop, and I'd like you to come up with an explanation of what the setup time is again, and we can discuss why this is important. So this is the old board we have been using on previous semesters. We'll skip that and look at our LX9 micro board, and I would suggest that now you could try to take your state machine design and you could use the 4 LEDs that we have. 2 of them are here and the other 2 are down here, and you can find the pins in the UCF file. You can use them to show what state we're in, and then you can use either these crappy dip switches, or you can attach some normal push button switches to the PMOD inputs and try to implement the state machine and see how it is to control in real life. Here's the user IOs for the LEDs and for the dip switches. You can pause if you want to create a UCF file based on these. Here are the PMOD IOs if you want to connect switches to any of the PMOD input pins. And again, you can pause with this slide if you want to create a UCF file based upon this table. It's also in the user manual for the board. Find out more. That's basically about reading chapter 5 and the beginning of chapter 6 in your FPGA Prototyping by Examples book, and get your hands dirty and find the ASMD PDF on Blackboard as well. That's it for now.